Alright guys, today we're going over Stoke's theorem, which is essentially a mathematical concept in vector calculus that describes a relationship between the surface integral of a curl of a vector field to the line integral of the same vector field over a boundary curve C. Okay, so this sounds very complicated, but in this video we're going to break this down and go over each individual part. To start, we're going to explain the line integral part. And to understand the line integral, we're going to start with this simple case in 2 dimensions where we have a vector field f. And essentially we're going to draw a path within this vector field. Okay, just a random path. We're going to call it C. So let's say we wanted to find the work done by the field on a particle that moves along this path. What we can do is divide this path into infinitesimally small pieces, right? Break them up into small displacement vectors. Right, so we can draw one, for example, like this. And this becomes our vector ds. Okay. If I were to enlarge it, and if I were to dot it with the force vector that's generated at this point, what we essentially find is the work done by a vector field along this small path. And if we were to find the integral of this dot product, what it's essentially doing is summing up the work done for each individual infinitesimally small portion of the path, summing all of them up until we have our full path. And what we end up having is something called circulation, right? And we're going to denote it with gamma here. And circulation is essentially just equal to this line integral, okay? And based off what we have deduced earlier, we can basically say that circulation is a measurement of the total work a vector field exerts along a certain path. To get us closer to Stoke's theorem, we're going to have to take this to 3 dimensions. So what I've done here is I've drawn another curve in 3 dimensions, but this time it's a path, it's a closed path, right? And essentially what this closed path is doing, denoted by C, is it's marking out the boundary of a 2D surface embedded in 3D space, right? So you can think of this as a surface or a piece of paper bent into 3 dimensions. So now what I've done is I've added a vector field. And in this case, for simplicity's sake, I'm just going to look at the vectors that are along this surface, right? Usually vector fields, you're going to have vectors in all of space, right? But for this instance, we only care about the vectors along this surface. And what we can do is find this line integral, or the circulation of this path, right? And we do it the same way we did our 2D case, right? We're just going to split this curve up into small displacement vectors ds, find the work done on each of them, and sum it up using our integral, right? And if you do the calculations, you'll find that our circulation in this case is actually equal to 0. So I'll kind of simplify it, right? We have some value of circulation here, but it gets canceled as you go the opposite direction here, right? We're going to assume that these are the same distance, okay? And as you traverse along these side lengths, you'll find that the vector field is constantly perpendicular for every ds along these 2 side lengths, right? And when you take the dot product of 2 perpendicular vectors, you're going to get 0, right? So these 2 cancel out and the side lengths are equal to 0, right? Our circulation is 0. What would happen if we were to look at a different case? We have the same closed path and the same surface, but this time we have a different vector field. What would happen if we were to calculate the circulation? From what you can see here, there's no cancellations, right? The vector field is always moving along the path, it seems like, right? It's almost pushing us along our path as we go along. And this means there's work exerted along every single infinitesimally small portion of our path, right? There's never a point where there's a perpendicular vector, right? So our dot product doesn't cancel. There's no cancellations. We have a non-zero circulation. See, now the cool part of this is if you compared the vector fields from the first and second case, you can see that if we look at the first case, we're going to see that there's no curl, right? All the vectors are the same magnitude. It's a little messy from the drawing, but assume that all the vectors here have the same magnitude and they're pointing in the same direction. If I were to put a ball in this vector field, there would be no rotation. If you look at the second case, you can obviously see there's some rotation going on, right? If I were to place a ball somewhere on this vector field, it would start to spin counterclockwise, right? So the curl for this second case is non-zero, right? So that's where you can kind of see where the Stokes theorem relationship starts to appear, right? In the first case, we have circulation equal to 0, and we also have curl equal to 0. And in the second case, we see that circulation is not equal to 0 and curl is not equal to 0. And this kind of intuitively makes sense. Right, when we looked at our second case here, we saw that this counterclockwise rotation, right, which is where we got a non-zero value of curl, this counterclockwise rotation was pushing us in the direction as we moved along our path, right? And this gave rise to our non-zero circulation. Right, you can see that the vector field is always applying some work along this path. And with this intuition, you kind of see that there's a relationship between curl and circulation. And what Stokes' theorem tells us is that they're essentially equal. This is Stokes' theorem's equation. We've already gone over the left part and what this means. So if we look at the right part, we know what curl is. If you don't know what curl is, you can watch my last video. And what dA is telling us is this dot product tells us that we only care about the curl along this surface. Okay, dA is an infinitesimally small portion of our surface, right? A small area, right? And that area has a normal vector that points perpendicular to the surface. And what we're doing when we dot the curl of this vector field with this dA is we're finding the component of curl that is only applicable to this surface area, right? Because we're not looking at the curl of the whole vector field. We are only caring about the vectors that are along this surface. Hopefully this video has helped you understand the intuition behind Stokes' theorem. Goodbye.